All right, this is our last section dealing with gases. Now, at the very beginning of this unit, when we talked about the kinetic molecular theory, we talked about there's three main points of the kinetic molecular theory that we need to remember. One of them is that the temperature is directly related to the kinetic energy. And then we also learned that the gas particles inside of the container take up so little space that we say that the volume is negligible. And then we also said that the attractions between the molecules also is negligible, that we pretend basically that they just bounce off of each other. Okay, however, those things, even though we assume that, in order for a gas to be what we call an ideal gas, so we've now learned the equation PV equals nRT, we know that based on that equation that the gas must behave as an ideal gas. Okay, and again, an ideal gas is a gas that does obey the kinetic molecular theory. And if it doesn't, then it's not an ideal gas. So today, the first thing we're going to talk about is we're going to talk about what basically constitutes a gas not being an ideal gas. So very commonly on the AP test is they'll ask you probably a multiple choice type question, but they'll ask you a question where they say, which of the following gases most likely deviates from ideal behavior? Or under what conditions would a gas not behave as an ideal gas? Things like that. So remember that the two things that we talked about with the kinetic molecular theory is that we pretend that the gases don't actually take up space inside of the container. Okay, if you have a container and you've got some gas particles inside that container, they do take up a little tiny bit of that space. Again, we pretend like they don't because there is a lot of space between the gas particles, but really they do take up a little bit of that space. Now, as you add more and more gas particles to that container, as you can see here, what happens is clearly now the gas particles are taking up more and more of that space. So when we talk about deviations from ideal behavior, we're talking about gases that do not behave like an ideal gas. And when would those conditions occur? Well, again, it goes back to those 2 points in the kinetic molecular theory, one of which says that gases don't take up any space inside the container. And again, as the pressure gets high, when you have a high pressure, we say that, okay, the more and more gas you put in there, the higher and higher the pressure gets. And as more and more gas particles get in there, the pressure gets higher and higher and higher, and they start taking up even more of that space. So the assumption that gases are composed of tiny particles whose size is negligible compared to the average distance between them begins to fail when the pressure is high. And this is because when the gas is at a high pressure, the gas particle size becomes more significant compared to the total volume. If this is a 5-liter container, let's say, we know that as you put more and more gas in there, that there's actually less and less of that 5 liters of actual empty space in there. And so as the pressure goes up and up and up, we know that the gas tends to deviate more and more and more from being an ideal gas. Okay, so therefore the actual total volume under these conditions is artificially large. So it seems bigger than it actually is. There might only be 4.8 liters of actual open space inside that container because now these gas particles that are in here are taking up a larger portion of that free space. So the actual total volume under these conditions is artificially large since the gas particles are now occupying a significant amount of that total volume. So as the pressure goes up, the gas particles start occupying more of a significant amount of that volume. Okay, so that's our one time that gases do deviate from ideal behaviors when the pressure is high. Okay, now another one that we talked about is we said that yes, gases don't take up any space inside the container, even though they actually do, and especially when the pressure is high. And then the other assumption we made with the kinetic molecular theory is that the molecules or the atoms of the gas are not attracted to each other. But we also know that that also does happen. And as the temperature rises and it has more and more energy, they bounce off of each other more and more, and they do tend to behave more like an ideal gas. Okay, more energy, the less likely they are to stick together. We know that water in the gas form turns back into a liquid as it cools. So as the temperature goes down, things become more attractive to each other. So the second way that gases deviate from ideal behavior is at low temperature. So the assumption that forces of attraction or repulsion between two gas particles are very weak, again, that's part of our assumption from the kinetic molecular theory, the KMT, the kinetic molecular theory, tells us, and the attraction repulsion isn't very strong, so let's just pretend like it's not even there. But as that temperature goes down, that idea begins to fail. Okay, this is again because at low temperatures, the gases have less energy. And again, just like out in the ocean, when the water evaporates, when it's nice and warm, and the water turns into gas, and then as it comes inland and it raises up into the sky, it cools off, it loses energy. And as it loses energy, it's more likely to join with other water molecules and turn into rain. So at lower temperature, the gas particles have less energy, so the particles are more attracted to each other at that lower energy. Again, just like water. And so therefore, the actual pressure is lower than one would expect. Now let's think about why. If the pressure is, let's say, 1.2 atmospheres, but we know that those molecules aren't hitting the wall as much as we think they are because they're actually being attracted to each other, that means that the pressure is actually going to be lower than what we think it should be. So the pressure is lower than one would expect because the particles are attracted to one another, and then they collide with the walls with less force. And again, that's what pressure is. It's how hard that the molecules are hitting the walls of the container with. Now, there's a lot of different ways that they can ask you questions about this. One of them, like we said, is they might just simply say, under what conditions is a gas most likely to not behave as an ideal gas? And they'll say, they'll give you a temperature and they'll give you a pressure. So you're looking for the highest pressure and the lowest temperature. And that's when it does not behave as an ideal gas. Okay? If the pressure is low and the temperature is high, that's when it does behave more like an ideal gas. So, and again, if you can wrap your brain around that, it's all from the kinetic molecular theory, that as the gas particles take up more space, as you add more gas to it and the pressure goes up, well, it's taking up more of that empty space inside. That makes sense why it would not behave like an ideal gas. And when the temperature's lower, they're more attracted to each other, so they're not going to hit the walls with as much force. Again, you can memorize this, or you can just learn, that why. Why is it high pressure and low temperature? Because then if they ask you a tricky question, you're not going to get tricked by it because you actually know why is it the high pressure and low temperature that causes it to not be act as an ideal gas. Now, later on in this unit, we are going to learn, notice the note here. Remember, those are important anytime you see a note. Later on in this unit, we're going to learn about what are called intermolecular forces. We've talked about this a little bit. We talked about the difference between intramolecular, which is a bond, and intermolecular, which is between one molecule and another. Okay, so later on, we're going to get into some more details about intermolecular forces between one gas molecule and another. Okay, and again, these are the forces of attraction between molecules. In terms of deviating from ideal behavior, a gas with stronger intermolecular forces will deviate more from ideal behavior. Because if there's stronger intermolecular forces, they're more attracted to other molecules. Okay, so it will deviate more from ideal behavior because the attractions between the molecules are stronger, similar to what happens when the temperature's low. When the temperature's low, they're more attracted to each other. So if two molecules, if SO2 has stronger intermolecular forces than Cl2, then we know that it's going to behave less like an ideal gas. So, for example, SO2 gas has stronger intermolecular forces. We haven't learned why yet, but it does, than oxygen gas does. So since SO2 is more attracted to itself, it's less likely to hit the walls with as much force, and therefore SO2 will behave less like an ideal gas than O2 will. So O2 will act more like an ideal gas than SO2 will. Okay, now, many times what this relates to, this relates to how fast the molecules are moving. Now, a lot of times when we talk about how fast something's moving, we talk about its speed. In terms of chemistry, the fancy term that they use to talk about how fast or slow a gas is moving is what we call the root mean square speed. And even here, the equation is U, and that stands for the speed, and RMS stands for root mean square. Now, you'll notice this equation is not given on the equation sheet, so you're not going to be asked to calculate the speed of one molecule versus another. However, we should be able to look at that equation. So really, in terms of this, what you need to remember from this is that is just the speed of a molecule or an atom, whatever. And then we have the number 3, which doesn't affect anything. We have the gas constant, which again is a constant. We're looking for things that can change. So there's 2 things in this equation here that can change. One of them is the temperature. Okay, the greater the temperature, the greater the speed. That makes sense. Okay, so if one gas is at 25 degrees Celsius, the other one's at 50 degrees Celsius, obviously the one at 50 is going to be moving faster. Now, this temperature, though, remember, has to be in Kelvin. Okay, this is not the Celsius temperature. So if I say 25 degrees Celsius and 50 degrees Celsius, well, is it going to be going twice as fast? No, for a couple reasons. Number 1, it's the square root. And then number 2, remember, 25 degrees Celsius is 298 Kelvin, and 50 Celsius is 323 Kelvin. Okay, that's not a 50% increase. So no, it will not be going twice as fast. Okay, so now typically that's not what they're gonna try to trip you up on. It's this bottom one right here, and that capital M, just like in the density and molar mass equation, that capital M stands for molar mass. Okay, now because it's in the denominator in that fraction, the molar mass, the greater the molar mass, the lower the root mean square speed. So if the molar mass is big, such as in, xenon, a xenon atom, which has a molar mass of 131, versus helium or neon or any of those lighter noble gases, xenon is going to have a much slower speed than helium or neon or any of those other gases. Okay, and how would you explain that on the test if you're asked to explain it? You would say because speed is determined by temperature and molar mass, and so if the temperatures are the same, you would just have to say the greater the molar mass, the smaller the root mean square speed. So the more massive, the larger the molecule is, and just that makes sense. I mean, typically you don't see really, really big people being able to run really, really fast. Okay, and typically bigger people are slower, and smaller people are faster. So similar with atoms and molecules, the lower the molar mass, the faster that molecule moves. Okay, so you should understand that at a higher temperature, a gas moves faster. Okay, temperature's on the top. And a gas with a lower molar mass will move faster than a gas with a higher molar mass. So greater temperature, greater speed. Lower molar mass, greater speed. Okay, lower temperature or greater molar mass, and the slower it goes. Now, this actually goes right along here with 2 terms that, again, you might see once or twice on the AP test. Okay, one of them is called effusion. Okay, effusion is the process in which a gas escapes from one vessel to another by passing through a very small opening. Now, what that means, usually that means like a balloon. Like if you take a balloon, you put a piece of tape on it, and you make a little hole in it, okay, the gases are going to start escaping. Okay, and even if it doesn't have a hole in it, the gases that, a balloon over time just shrinks, and we know that the gas that's going to escape first is, this is a process called effusion, and we're going to talk about what the process is, what gases are going to escape first. Okay, and then our second one here is called diffusion. That's actually a term used in biology quite often, the diffusion of a chemical through a cell wall. Okay, but that is the process by which a homogeneous mixture is formed by the random mixing of two different gases. Basically, it's like when you put, cologne or perfume on and you spray it, and then it slowly spreads out throughout the room. Okay, that's diffusion. As you're going from a high concentration of something, you spray that cologne. There's a high concentration right there in front of you, and then it slowly spreads out throughout the room. Okay, that's the process of diffusion, is a gas basically traveling a certain distance over time. Okay, now Graham's law, which again involves effusion and diffusion, states that the rate of effusion or diffusion of two gases is inversely proportional to the square roots of their respective densities and molar masses. We don't need to, there's an equation that goes with that I didn't even write on here. You don't even need to remember that. So the equation for Graham's law is not given on the equation sheet. However, you should appreciate and understand that the smaller the molar mass of the gas particles, the faster they move. Okay? And again, that comes back to this equation up here, the root mean square speed equation, that the smaller the molar mass, the faster they're moving. So which one's going to escape out of a balloon faster? Which one's going to escape through a pin-sized hole? That's a lot of times the term they use on the AP test, is a pin-sized hole for effusion. Which one's going to escape out of the pin-sized hole faster? Is the one that has the lower molar mass, because it's moving faster and it's more likely to go through that hole quicker than one that's not moving as fast. Okay, and diffusion is the same thing. The smaller the molar mass of the gas particles, the faster those molecules are moving, and therefore the faster they're going to effuse and diffuse. Okay, for example, helium escapes through a pinhole-sized leak in a balloon faster than oxygen does. And how would you explain that on the AP test? Simply because helium has a smaller molar mass than oxygen does, and helium therefore is moving faster than oxygen does, and so it's going to effuse, and here we can also see helium diffuses faster than oxygen does for that exact same reason. So effusion and diffusion are related absolutely to this root mean square speed equation. Okay, which again is not given on the test. You just need to remember that greater the temperature, the greater the speed, which means greater the temperature, the greater the effusion and diffusion. And then smaller the molar mass, the greater the speed, and therefore smaller the molar mass, the greater the rate of effusion and greater the rate of diffusion. And really, that's really all of those three things are tied very closely together, and they're all just based on that idea of temperature and molar mass are what determine how quickly or slowly a gas will move. All right, the last little bit here deals with solubility of gases. So if you have a solution like a 2-liter of Coke or something like that, you've got a closed 2-liter, and gas is filling that space above it. So you've got a 2-liter bottle where we know that here at the top, and I'm just going to draw the top part here. Okay, we know the Coke only comes up to here. Well, clearly there is we've got some empty space here where you've got some gas particles. Now, the gas particles could be air from before they close the lid. It could be that some of this carbonation comes up, some of that CO2 comes up into that area. And we know that at a high pressure, there's more gas particles that strike the surface of the solution and enter the solvent. Okay, when the pressure is high, that's what happens. Which means that the concentration of the gas dissolved in the solvent, so remember the solvent is water, and in this case, the gas is the CO2, that the concentration of the gas dissolved in the solvent is greater than if the pressure were low. So what that leads us to is that gas solubility usually decreases with an increase in temperature. Now, typically that doesn't occur. Think about when you dissolve sugar in water. Okay, if you're just trying to dissolve sugar in water, one of the ways to make the sugar dissolve better is by increasing the temperature of the water. You know, if you've ever made like homemade syrup, when you make homemade syrup, you get the water really, really hot and you can add more and more sugar to it. Okay, typically solids are more soluble when the temperature of the solvent, the water, is high. Okay, but gases, think about that. If you have a warm bottle of pop and you take that lid off, and all of a sudden the stuff goes squirting everywhere. Okay, that's because the pressure inside of there is very high, because at an increase in temperature, the solubility of the gas decreases. Okay, which means the gas doesn't stay dissolved in the water as well, which means this pressure up in this space is really, really high. So all of a sudden you release that pressure, and the gas and some of the pop on the top comes squirting out. Okay, that's also the same reason why when you shake it up, well, when you shake up the gas or you shake up the pop, the same thing happens. Is all of a sudden you've added a lot of energy to that solution, and more of that CO2 has been able to escape. So now once again, you've got a container that's very, very high in pressure because you've added energy to that solution, and the CO2 has been able to escape. So you've got a really high pressure. Again, you open the lid and it sprays everywhere. Okay, the best way to open the pop, and if you like really carbonated pop, you want it I don't want it flat. I want as much CO2 in there as possible. You want the water to be cold, or the solution, the pop to be cold, and you want it to not have moved very much. You want it to be nice and settled. So get it nice and cold, and then don't have it moving around a bunch, and then when you open it, you shouldn't have as many molecules of CO2 up in here, so it won't spray everywhere. So solids in general, when the temperature goes up, it becomes more soluble. It dissolves better. Okay, but with gases, it's the opposite. Okay, the higher the temperature, the less that gas, the more energy you're giving that solution, and so the more the gas is going to escape. And again, that's why many times if you drink pop that's warm, it doesn't taste as carbonated. Well, because it really isn't as carbonated. And so that, certainly makes it so, again, if you like the taste of carbonation, it doesn't taste as good as if it were cold. So gas solubility decreases with an increase in the temperature of the solvent, or of the solution, I guess, okay? Now, the particles, again, the gas particles have more energy. They can escape from the solvent easier, which means, again, that less gas is dissolved in the solution. Now, you'll notice here, this is kind of the end of gases, and then after this, we are going to get into solutions. So this is a good place to stop for today. So just a quick review here of what we've gone over. So we first started talking about deviations from ideal behavior, and then we know that when gases are in an ideal condition, we don't say that they take up any space and that they aren't attracted to each other, but we know that when the pressure is high and the temperature is low, they are attracted to each other more, and they do take up more of that space. We know that the stronger the intermolecular forces, the more a gas will deviate from ideal behavior. We know that a gas, the speed of a gas depends on the temperature of the gas and the molar mass of the gas, and the smaller the molar mass, the greater the speed, and how that relates to effusion and diffusion. And then we talked about how the warmer a solution is, the less soluble a gas is. And that's it for gases.